All right, hi guys. So in this video, I'm going to talk about osmosis and tonicity. Miss Lay just pointed out that I'm talking kind of fast, so I think that on YouTube there is a feature where you can slow down the video. You can set it to like 0.7 speed, so you can do that if I'm talking too fast. I'm sorry if I'm talking too fast. Okay, so osmosis, I think you've heard that word before. You did stuff with that for Hinton Bridge this summer. It's the diffusion of water, so the movement of water. That's what osmosis is. So for example, in this situation, we're starting with two sets of fluid that are divided by a membrane. That's what my black dotted line is supposed to represent. One has a concentration of 1 molar, one has a concentration of 3 molar. You might recognize that from chemistry class. If you don't, that's okay. Just know that 1 is less than 3. So the water molecules want to make these concentrations have an equal, make these solutions have an equal concentration. So this one has is less concentrated, this one is more concentrated, so the water needs to move from the less concentrated one to the more concentrated one to dilute it a little so that they're equal. So once that water moves over, we can have two equal concentrations. So for example, maybe 2 molar and 2 molar because the water moved over. That's what we call equilibrium, when the concentrations on either side of the membrane are equal because the water has moved to make it to be equal, make it at equilibrium. Your book has some pictures that look like this that I think are pretty great. So if this was our starting condition where we have 3 sugar molecules or whatever are dissolved in our liquid on this side and only 1 on this side, the water moves from the less concentrated side to the more concentrated side. And this clearly shows us that there ends up being more water on, we'll call it side A and side B. There ends up being more water on side B than on side A because all of that water needed to move over to be able to make these concentrations equal. The sugar molecules can't cross this barrier. Okay, tonicity is the ability of a solution to cause a cell to gain or lose water. So what does that mean? There's 3 states of different types of tonicity, different types of tonicity. Let's see if I can make this straight. So, for example, if something is hypotonic, that means that the surroundings have less solute, so the water is going to rush into the cell. So you can kind of see that from the picture. So this cell just exploded because there was so much water that rushed into it that it couldn't handle it anymore. It exploded. This is a red blood cell. In this cell, this is a plant cell, you can see that the cell wall is buckling because there's so much water that's rushing in. So water's rushing in, water's rushing in. And that's because the surroundings, the outside of the cell, like this liquid around the cell, has less solute, so it's less concentrated, so the water is going into the area that's more concentrated. If something is isotonic, that means it has the same tonicity. So iso is same, hypo is low, hyper is high. Isotonic, again, it's the same concentration, so the water is going inside, but it's also going outside. So it's at an equilibrium. It's flowing in and out. It's not changing the concentration. So the surroundings have the same solute concentration. Hypertonic, hyper means extra, so the surroundings have more solute, so that means that water is leaving the cells. So in the case of our red blood cell, it's getting shriveled up because the water is leaving. In the case of our plant cell, it's also shriveling and pulling away from the cell wall because the water is leaving. If a solution has more solute, water tries to go in to dilute it. So that's the take-home of tonicity. You're also going to see problems that have to do with water potential, not on the worksheets that you're doing this weekend, but when we get back together, and I just wanted to kind of give you a quick introduction to it. So water potential is all about the potential for water to move from one environment to another environment. This equation, as well as this one down here, are both on your formula sheet. I'm going to grab it to prove it to you. So right here, there's stuff about water potential. So it tells you what the different variables mean, and it gives you a little blurb about it. I know you can't read it really in the video, but you have one. So it's there. You have access to it, and you'll have access to it on the exam. So again, water potential is about the potential for water to move from one solution to another solution. I think we just have the lines forever. All right. So for example, in this situation where there's a beaker with a 0.1 molar solution and a cell inside that has a 0.2 molar solution, this one is more concentrated than the outside. So the potential for water is the water wants to move inside the cell. So there's potential for water to change, to move, because there's a discrepancy in the concentrations. So in this case, the water is leaving the more concentrated, no, actually I think I did this wrong. Yes, I did. This cell should be exploding. This is less concentrated, right? So the water is going to move in here to try to dilute the cell. So this cell is going to be an exploding cell, not a shriveling cell. When the concentration of the cell and the concentration of the beaker are the same, we will say that there is an equilibrium, and that means that the water potential of the beaker is equal to the water potential of the cell. So the potential for them to move around is equal at this point because they're at equilibrium. So when we're back together, we're going to talk about this equation as well. So you can solve for the potential solute using this equation. And I think I'm actually just going to wait and talk to you guys about it when I see you again.